Hello, Honors Chemistry, and welcome to Chapter 5, Sections 5.5 through 5.7, where we work on naming and writing formulas for ionic compounds. All right, so previously we talked about how to identify them, right? Like first we're looking for, is it ionic? Is it type 1 or type 2? And then is it binary or polyatomic from there, right? Because then that's going to give us guidance for how to name them, right? Based on ding, 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 right? This chart, right? So first what we're going to do is we're just going to look at some ionic compound names and formulas, right? To pick up on some trends. And then I think if we just pay attention to the naming system that we see, right? Then I think applying it becomes a little bit easier, right? So if we look here, right? We have 4 different ionic compounds, right? We will note that all of them, right? So all of them are what type? Right, so they're all binary. And then let's narrow them down. How do we know they're ionic, first of all? Right, so we would go look at our periodic table. We would find sodium is a metal, right? Chlorine is a nonmetal, right? We would go find that potassium is a metal, nitrogen is a nonmetal. And so for both of those two, right, we would see that those metals fall into the, right, type 1 category, right? So these would be type 1 binary. Now if we look here, right, so these, we have iron and oxygen, copper and iodine, iron and oxygen, copper and iodine. So we still have metal and nonmetal, right, which makes us ionic. Now though, our metals are the, right, type 2 variety. So these would be type 2 binary. Right, so we have identified those, right? Now we just need to look for some other similarities, right? We'll see that when we look at their names, right? Sodium chloride, potassium nitride, iron oxide, copper iodide. What do we notice? Right, they all end in "ide," right? And that's what this table is telling you, right? That basically for our nonmetals in a binary compound, what we do is we just take the root and we add "ide" to the end, right? So these are your roots, and then we would add "ide," right? So in here, right, for our type 1 binary and for our type 2 binaries, right, they will always be root and then "ide," yes? That's how they are named, yes? All right, for the cation part, right, we'll see sodium, potassium, iron, copper. Right, we're just using the full name of that cation, right? No amendments, no changes, just the full name, right? And then we'll see, right, what is different between these two sets. Right, we'll see that for the type 2, right, we have this special inclusion of a number in Roman numerals, right? And that is the charge of the metal, yes? That is the charge of the metal. Nope, not here. So charge of metal in Roman numerals. Okay, yes, does that make sense, right? So if we look at a type 1 binary versus a type 2 binary, right, that charge is the only thing that differentiates one from the other, yes? As in you can't tell the difference any other way, right? That's it, right? Otherwise, their full name of the cation comes first. They all end with a root plus "ide" of that anion, and the only distinguishing feature, right, is that charge of the metal in Roman numerals, right? So when we go back here, right, that should make sense, right? As in these two look different because there's a charge there, right? These don't have a charge because they're type 1s, okay? Now, in terms of how to write the formula, so I did not include that on this chart, but how to write the formula for an ionic compound is always about charge, yes? And not just charge, right, but the magnitude of positive charge must equal the magnitude of negative charge, yes? The magnitude of your positive must equal the magnitude of your negative, right? Which means that it just becomes like a math problem at that point, right? And when we use the word magnitude specifically, all we're doing is we are taking out and doing basically an absolute value of the charge. Yes, does that make sense? As in, it doesn't matter that one says plus and one says minus, right? We just need the magnitudes to be the same, right? And so if we work through a couple of these together just to confirm that indeed the magnitudes are the same, right? First, we need to go figure out their charges, right? So sodium, right? So the perk of type 1s are that the charges are based on their location, right? So for sodium, right, has a charge of +1 based on the fact that it's in group 1, right? And chlorine has a charge of -1 based on its location, because remember that these are -1, these are -2, right? These are -3 based on how many valence electrons they have and how many they take when they undergo a chemical reaction, yes? All right, so then if sodium chloride has, if this has a charge of +1 and this has a charge of -1, right? I need the magnitude of the positive to equal the magnitude of the negative. And I would make that happen by using subscripts, which tell us how many of each ion are necessary to make this condition be true, okay? So that's like saying 1 times what is equal to 1 times what? And I think clearly the answer is 1 of each of these ions, which is why there's an implied subscript of 1 for each of those ions, yes? Potassium nitride, so let's go back and find potassium and nitrogen. Potassium is also group 1, nitrogen is one of these -3s, right? So this is +1 -3, right? So that's like saying I have a 1 and I have a 3, and how do I make those magnitudes equal? Right, I'm going to have to put a 3 here and a 1 here. So that means I need 3 potassiums for every 1 nitrogen to make the magnitude of positive equal the magnitude of negative, yes? All right, now let's go ahead and do the iron oxide example, right? So here, right, again, what is this? Right, that's the charge of the iron. So I already know that iron has a charge of +3. Now I have to go find oxide, which means it came from oxygen. So let's go find oxygen. That's one of our -2s. So I have a 3 and I have a 2. And I need to, again, make the magnitude of positive equal the magnitude of negative, right? And so that means if I had 2 of these and 3 of these, so 2 irons and 3 oxygens would give us a magnitude of positive that equals the magnitude of negative, yes? And that's where our 2 and 3 come from. Same thing here, right? Copper iodide, right? Copper has a charge of +2. Iodide comes from iodine. Oops. Which is right here. So that's a -1. So same thing, 2, 1, and then I just need to fill in my subscripts, right? Like that. And so you'll note that I always set mine up the exact same way, right? I always put the charge or the magnitude of the charge in parentheses, right? And I'll use a line, right, for where I'm going to put the actual subscript relationships. Because if you always set it up the same way, you're more likely to do it correctly, right? Now, another thing to keep in mind is that for some of you guys, right, you might just be able to look at these charges and be like, oh, yeah, all we're doing is finding the lowest common multiple, really. I think that's the right word. Lowest common multiple, and so what subscripts do I need to get there? And if you can do that in your head, perfectly fine. You don't need to write out the math to do it, right? Just that if you aren't one of those people that just sort of sees that relationship in your head, then write it out, right? It takes like 2 seconds, and it'll get you the right answer. Yes? Does that make sense? All right. Thank you for listening. Be good. I will see you soon, and stay tuned in the next video where we talk about ionics, specifically polyatomic ions. All right. Thanks for listening. Be good, and I'll see you soon. Bye.